Fourier series and what happens when I get relatively similar waveforms and what is the difference of the coefficients. And I want to talk a little bit about how do certain structures kind of behave a little better with certain coefficients than others. So to start it off with, we start with two signals, very common, see them all the time. One is basically a square wave. This is going to be a period of 4 milliseconds, and a triangle wave where I have a period of, again, 4 milliseconds. What's really nice with both of these, because they're centered around 0, so I'm guaranteeing that any Fourier series coefficients, that the DC point, the A0 term is 0 because I'm centered around 0. We could have done something where it would have been, well, hey, could have been a little bit less, could have been something with an offset, but it doesn't really help the conversation here. And what's really interesting is that we can actually sit down and actually do the Fourier series for these two cases. Now, the one thing that's really nice about the way I centered this one is that it sets up having a very even function. So we know that this is going to eventually be cosines. And it's eventually also going to be cosines of k pi t over 2, where t is in milliseconds, for k is odd, which is going to be kind of a nice form. But you can actually see this by setting up for the a sub k. It turns out that the sine terms will disappear because this has this nice symmetry. And you can kind of work your way through the integral, normalize the time. You get this fun integral here, but you realize the 3 to minus 1 is a 1 to minus 1, but double it effectively. And it gives you this sort of 4 over k pi with an alternating sign. So what that means is that my x of t is really a sum of k odd of these terms, cosine of there. And so your terms are 4 over pi, minus 4 over 3 pi, 4 over 5 pi, minus 4 over 7 pi. What's really interesting is when you look at the waveform, and I just took it over here, but I actually plot the first 4 coefficients, you realize you actually have a pretty good approximation, although you've got a little bit of wiggliness at each of the top edges, but not bad to start with. I mean, this gets you quite a ways into what the function's looking like. You have your coefficients, again, on the various parts. So the primary harmonic is 250 hertz, because, again, your T0 is 4 milliseconds, so it has to be 1 over that as your frequency. Then it's 3 times it at 750, 5 times it at 1K plus 250, so 2500, and then at 7, which is 1750 hertz. So that's what your coefficients look like. Interesting question, though, how to look at the solution for this one. And we can certainly notice here we've got an odd symmetry. We could actually do a number of pieces and do the same kind of integral. But another way to approach this is to realize that this is the integral of the square wave above. And you think, that's kind of interesting. So if I were to integrate just my solution over cosines, well, that's going to give me, I'm going to get 8 over pi squared, and then I get an alternating, the same alternating term, but now I got a k squared. So the coefficients are now going to the same sort of position and frequency. There's only going to be odd terms, not even terms, but now it's 8 over pi squared minus 8 over 9 pi squared. Notice how fast these drop. And so once I've gotten to this, to this fifth term, I realize that the next term is maybe 2% of the energy, and then it gets even smaller and smaller. And in fact, you look at the waveform of the triangle waveform and the coefficients in there, and it maps really, really closely with just the first 3. I didn't even bring the 4th one in there. Yes, you'll see a little bit of a bounce on the edge there. Other than that, it looks really good. And this is one of those interesting properties. Well, it's an interesting question then. You say, well, let's say I've got a system where I need to sample. Let's say I needed to sample at 3 kilohertz, which would put my Nyquist right in the middle here, which would mean that this term would get aliased, and this term would get aliased. Well, how devastating is that? Well, this is actually going to be pretty significant, where this one's pretty weak in terms of what you would have. And so that would actually be pretty cool, because you could still then take this and reconstruct it back to this form. How? Take a derivative. Take a derivative numerically in the digital system and you're good to go. It's interesting to kind of see how these things play back and forth and how you can get kind of different functions. But it's also interesting that with the Fourier series, you get some very simple operations that allow you to do some of these very, let's say, complicated calculations pretty quickly.